Good day, viewers. I am creating these videos to help teachers of mathematics support their learners in making sense of mathematical concepts and their associated procedures and processes. And today what I want to look at is expanding linear expressions. And I have my algebra tiles out to help me with that. So let's say I want to look at an expression, something like 5 times 2x plus 3. Well, the way I'm going to help learners make sense of that, and hopefully they will already have some experience of multiplication as an area for this, is to multiply these two factors to create an area. And what that's going to look like, and I've set up my horizontal and vertical, as you can see there, what that's going to look like is build me a rectangle with a width of 5 and a length of 2x plus 3 without any gaps or any overlaps that would fill this space. Now, of course, not this whole space, but the space outlined by the 2x plus 3 along the top and the 5 along the bottom. Now, the first time learners meet this, what you'll almost certainly get is immediately trying to put ones in here. And of course, this is the beauty of our x rods. Our x rods, you can see the ones will not line up perfectly with those. So very quickly, pupils will become disabused with that idea. And so what we'll get to instead is the idea, well, I can put a 1 by x there, and I can do the same there. And actually, I can fill all of this space with x tiles, with 1 by x tiles. And then similarly over here, I can fill this space with 1 tiles, because these are in effect just little 1 by 1 squares. And then I can look at how many of these have I used. Well, clearly here, because I've got 2 x's by 5 ones, I'm going to have 5 rows of 2x, and so that's going to result in 10 x's. And then similarly, if I've got 3 ones by 5 ones, well, this is just a 3 by 5 rectangle here, and that's a 3 by 5 makes 15. 3 rows of 5, or 3 columns of 5, sorry, in that case makes 15, or 5 rows of 3 makes 15. So as well as that 10x, I have 15. And of course, if we want a partial abstraction before we go straight from here to there, well, we should be able to see that this is the beginnings of drawing a grid. So I might actually draw a picture of that to look a little something like this, where I can say, well, I've got this rectangle that represents the area that has a width of 5 and a length of 2x plus 3. But I can see that actually that rectangle comes in 2 parts. It comes in what is seen here, a green part and a yellow part, where the green part is the 5 by 2x bit, and that gives me 10x. And one would hope, of course, that learners have a bit of experience in multiplying terms before they come to expanding brackets, so they can see that 5 times 2x will give 10x. And similarly, this will give 5 times 3, which is 15. But I know from perhaps previous study of area that if I have 2 areas and I want to find the total area, that I just add the 2 separate areas together. So 10x and 15. What happens then if I want to change one of these to be negative? So if I have, say, 5 lots of 2x minus 3, well, I mean, some people don't like this because they don't like the concept of negative area, but it is possible to represent it using the algebra tiles. If I flip each of these 3 to become a negative 3, Then there's a couple of different ways that I might explain this. I might, and assuming pupils already have a sort of prerequisite understanding of multiplying negatives here, I might be able to see that a -1 times a 1 will result in a -1. But actually what I can do in this representation is say, well, because this tile has been flipped, that is going to flip everything in its column. So I can flip all of these. And then similarly, because this tile has been flipped, that's going to flip everything in its column. And sort of there's a process with this, if you like, which is not a process, it's just, or not really a process, it's just a result of knowledge of multiplication of positive and negative numbers. But the idea would be broadly that if anything in a row or column is flipped, then everything, or if anything around the outside of a row or column is flipped, then everything inside is flipped as well. So the fact that this -1 at the top of this column is flipped, flips everything in that column. Okay, and similarly for the other two. And so I can see quite clearly there now that the first part of that rectangle, the 5 by 2x, hasn't changed. That's still going to give me not 2x. That's going to give me 10x. But the act of flipping this +3 to be a -3 has flipped the sign of the area that's underneath it. And so I have -15. And I can even do that then with the factor in front of the bracket. I could say, well, what happens if I flip that -5? But keep that the same. Well, now, of course, because I am flipping this 1 into a -1, everything in this row is going to flip. Or I know that -1 times x gives -x, but then so does this. But then -1 times -1 gives 1, and I'm going to continue to flip everything in that row. And then similarly, because I flipped that, I will flip everything in this row. And then so on, working down. And then I'm going to cheat a little bit here, and rather than flip these things, I'm just going to copy them down. Oh, hello. Then the ones don't copy on top of the -1s. There we are. The ones copy underneath. But there we go. And I can see now, because I've flipped this, I've flipped everything here and everything here and everything here. And so now I can see, well, because this was -5 times 2x, that gave me the -10x. But because that was -5 times -3, the -3 had flipped these all negative when it was here. But now I've flipped all these negatives. They've in effect flipped back. So they're back to +15 again. And again, I could be drawing, different area models for those things as a way of partially abstracting this. So I can go from the concrete to the pictorial to the abstract and back again, or work between them flexibly as I need to. So that is just a short video on how we might look at expanding linear expressions and using the algebra tiles to support in doing that. As always, I'd like to say a big thank you to mathsbot.com and its creator, Jonathan Hall, for the wonderful website that he's put together for us. And if you've never been on mathsbot.com before, I very much recommend that you take some time to check it out. Not only has it got a load of wonderful virtual manipulatives that I've been using to create these videos, but there's all sorts of other completely free resources on that site to help teachers of maths with their teaching and support their learners. And if you are interested in using visuals and manipulatives to support teaching of mathematics, then I would also urge you to check out my website, visiblemaths.co.uk, where amongst many other things that you'll find on my website, you will also find a link to the publisher of my book, Visible Maths. And the publisher is Crown House Publishing, and there's a link on the website there where you can view some sample pages, and if it looks like something that might be useful for you, you can of course place an order. I'll be making these videos throughout lockdown and potentially even beyond. So if there is a particular mathematical concept that you think you would like to see how that would work using manipulatives or visuals, then please do get in touch and let me know what it would be, and I will do my best to provide it for you. Thank you very much, ladies and gentlemen, for your kind attention.